All right, we're going to get started in just a couple minutes.
Okay, we'll go ahead and get started. Let's see here. Welcome everyone to today's edition of the Keller North America webinar series. My name is Jim Husson. I'm a director with Keller North America and the host of today's session. These webinars have been held quarterly, and this is the final presentation of 2021. The attendees today will receive information on 2022 webinars closer to the events. We trust that you will find today's presentation entitled Liquefaction Mitigation by Ground Improvement, a focus on mechanisms and design, both informative and enjoyable. A few items before we get started. All attendees are muted to avoid feedback and enable everyone to hear the presentation, but questions are welcome. Questions can be submitted through the chat window and will be answered at the end of the presentation. Due to the large number of attendees, there will likely not be time to answer all the questions live, so unanswered questions will be addressed in a follow-up email. Also, please note that this session is being recorded. Lastly, a 1-hour PDH credit is available for attending this session. To request the PDH credit, please complete and submit the form, which will be posted in the chat at the end of the presentation. And now I'd like to introduce our speaker for today. James Gingery, PhD, PE, is a chief engineer for Keller and has over 25 years of experience in geotechnical earthquake engineering for water, energy, transportation, industrial, commercial, and residential projects. Dr. Gingery has specialized expertise in liquefaction and lateral spreading, ground improvement design, and numerical modeling of soil and soil structure interaction problems. He's published more than 24 technical papers for journals and conferences. He holds an MS in geotechnical engineering from UC Berkeley and a PhD in geotechnical earthquake engineering from UC San Diego. In 2015, he was awarded the Shamshir Prakash Prize for Excellence in Practice of Geotechnical Engineering. I will now turn over the presentation to Dr. Gingery for his presentation. Thank you. Take it away, Jim.
Thanks, Jim. All right, well, thanks everybody for joining today. We're going to blast through this material pretty quickly. I know you may have some questions, and there's certainly a lot more detail that goes into this, but this is what we can cover in an hour, and I hope you find it helpful. Here's the agenda. We're going to talk about key elements of liquefaction, common ground improvement techniques for mitigation of liquefaction, design of ground improvement, and then hopefully some time for Q&A at the end here. So first we'll get into the key elements of liquefaction. So there are three important things that we want to consider when we're looking at liquefaction. It's sort of like the three ingredients that are necessary in order for it to occur. One is that the soil composition needs to be amenable to liquefaction. Is it a soil type that is compositionally liquefiable? Number two is the state of the soil and the loading. Is the state loose enough and the loading from the seismic event strong enough to generate liquefaction if it meets the compositional criteria. And then lastly, what are the engineering consequences of liquefaction? We don't necessarily care that liquefaction happens or not. We care about the consequences of the liquefaction in terms of how they affect our engineered structures. So first, the compositional criteria. There have been several criteria that have been proposed. Bransancio 2006, PI and water content liquid limit criteria. The Idris and Boulanger 2008, PI-based criteria, and some adaptations of these things from Armstrong and Malvik. There's a relatively new criteria called the Delta Q system from Say et al. 2021 that's still kind of new and being considered, starting to be considered. And then for CPT-based analysis, we typically use an I sub C based criteria, but all of these criteria are available, and generally we're talking about threshold PIs between 7 and 12, and a threshold I sub C of around 2.6 plus or minus. For the state and the loading, I think a lot of us are familiar with this. I don't have time to go into too much detail if you're not familiar with this. But we calculate a factor of safety against liquefaction. It's the ratio of the cyclic resistance ratio to the cyclic stress ratio. Typically, we normalize it by an earthquake magnitude of 7.5 and an overburden stress of 1 atmosphere. Cyclic resistance ratios are largely based on empirical data and practice, where we use a CPT or an SPT penetration resistance to determine or estimate the cyclic resistance ratio. That's basically the cyclic strength of the material. And then for the cyclic stress ratio, using the simplified method, we use the peak ground acceleration, a stress reduction factor, factors that account for the magnitude and the overburden stress and the stress conditions in the site to determine what the cyclic stress ratio is using the simplified method. So for the engineering consequences, these are the kinds of things that we're talking about. There's a lot of focus in liquefaction analysis and in ground improvement design on settlements. And when we talk about settlements, they come in different forms, but most people think of the volumetric settlements, the post-reconsolidation settlements that happen when excess pore water pressure is dissipated. And here's an example of that from a building that was founded on a pile foundation, and that's where a pile cap is, but the slab was just on grade. So when the liquefaction occurred and the ground settled, where the slab was just sitting on grade, it settled by 4 to 6 inches, and it kind of draped up over the pile caps that didn't settle because the piles extended down below the liquefiable layers. Settlements are important, but bearing capacity is probably even more important, because with volumetric settlements, we're talking about displacements on the order of inches, but with bearing capacity, we can be talking about displacements or penetrations into the ground on the order of feet or meters, and the possibility of the structure tilting over or collapsing. So I really encourage people to think about bearing capacity as an engineering consequence, and I'll touch on that a little bit in the presentation. We have lateral spreading and flow failure. These are phenomena where we have mostly lateral displacements. Lateral spreading is sort of like a ratcheting towards a free face or down a gentle slope. A flow failure can occur when the static driving stresses exceed the resistance from the liquefied soil after it liquefies. An example of that from the 1971 San Fernando earthquake with the lower San Fernando dam. And then surface manifestations are where we have sand boils and ejecta coming to the surface, ground cracking, things that can be disruptive and generate more settlements or other kinds of ground displacements. So common ground improvement techniques for liquefaction mitigation. So when we think about ground improvement techniques, we want to think about how they're acting on these elements of what makes the soil liquefiable, which is the composition and the soil state and the loading. So for composition, we can affect that by solidifying the soil and we can use basically techniques to introduce cement into the soil and make it a solid that's no longer compositionally liquefiable. For the state, we can densify the soil. We're not changing the composition of the soil, we're just changing its state, and we're trying to render it to a state that's denser and under the given loading would be liquefiable. And then with loading, we can try to reinforce the ground so that we reduce the loading on the soil by taking it up more so with the ground improvement. So these three techniques are solidification, densification, and reinforcement, and that's how ground improvement can act on, primarily can act on to mitigate liquefaction. We also have drainage. That's a secondary kind of effect that can be also considered. So vibrostone columns are a very popular method for liquefaction mitigation. With this technique, we're using a depth vibrator that penetrates into the ground with or without pre-drilling. In the bottom feed technique, we use gravel that's placed in a hopper, it goes down a tube, it's injected at the bottom, and the vibrator, it works up and down to push the gravel out into the ground laterally, compact the ground by that expanding bulb and by the vibration of the vibrator, and form a column that also reinforces the ground. So primarily we're getting densification of the soil between the stone columns, and we're getting a dense stone column rather constructed, but we're also getting a little bit of reinforcement of these of the ground due to the stone columns, and the relative cost for that technique is low. For vibrocompaction, we're talking about a similar technique where, but instead of introducing gravel, we're going to use the clean sands that are either available at the site and can cave in from the sidewalls, or can be fed from the top using a top feed method. This is very similar, but it doesn't require the stone. It requires a clean sand generally to at the site, like a nice clean beach sand. And in this method, we're just purely densifying the soil. Deep soil mixing is a very powerful technique where we take a large drill rig, we equip it with a mixing tool instead of an auger, and that mixing tool introduces a binder. It's usually cement, Portland cement grout. Can have other cementatious agents in it as well, like slag, and it's mixed in with the soil, and it basically changes the soil from soil to a soilcrete. And this method is, can be constructed using columns or overlapping columns to create panels and grids. One thing to know about it is it generates spoils because whatever volume of grout that you introduce into the ground comes out as spoils. Generally, that's about 35% of the treatment volume. And we're using, again, solidification. And if you put them into certain configurations like panels and grids, then we can reinforce the soil as well. Jet grouting is a technique sort of similar to deep soil mixing, except that instead of mechanical mixing with blades, we're using erosion. We're using a high velocity jet of grout to erode the soils and mix them together to form the soilcrete. This technique generates more spoils compared to soil mixing. It's generally more expensive, but it can be very effective if you need to target a particular zone at great depth, so you don't have to mix all the way from the top to the bottom. You can go down and treat a zone that's targeted. If you need to work around obstructions like piles in the ground or other need to form different shapes, then this can be a really effective technique. Compaction grouting is a method where we drill a hole into the ground. We insert pipes to the bottom of the hole, and then we pump a low slump grout into the ground and form these expanding bulbs that push laterally and compact the soil adjacent to it. You may put this in a grid of columns all around to compact the soil that's between the bulbs. This is a densification technique that works on sands and silty sands. Cost is sort of moderate. And one thing to be aware of is that you need a certain amount of overburden stress so that the expanding bulb pushes into the ground horizontally instead of heaving the ground. If you get close to the surface, say, I don't know, 10, 15 feet from the surface, the vertical stresses are not sufficient to keep the ground from heaving. So you generally can't get very much compaction close to the ground surface, and that's a limitation of this technique. Deep dynamic compaction is a method where we use a specialty crane to raise a weight that's 10 to 30 tons. We drop it anywhere up to 100 feet from the ground surface in grid patterns that range in spacing from 7 to 25 feet. You basically just pound the ground and densify the soil through that dynamic compaction method. At about 30 feet or so below the ground surface, that's where the effect starts to, is tapering off by 30 feet. And the thing to keep in mind here is that it generates a fair amount of noise and vibration. So it's typically a technique that you're not going to use in a dense urban environment. You need, some setback. But we have ways of working around that. Some sites that are very large, for instance, we might do DDC wherever we can, or wherever we can, and where we get closer to, people that are sensitive to the noise or vibration, we might switch to another technique like vibrostone columns that has less noise. Okay, so this table kind of summarizes the methods that I went through and whether they're acting by densification, reinforcement, solidification, the types of soils that they're effective in, the relative cost, and the relative frequency of use. And that's based on our experience here, mostly in the Western US, where we do most of our liquefaction mitigation. Okay, so design of ground improvement. The two major mechanisms that we're talking about today are densification and reinforcement. So if I have a site that's liquefiable, it means that I have a cyclic stress ratio that's up here greater than the cyclic resistance ratio that's represented by this black line. So the red zone is liquefiable, the green zone is not liquefiable. And I want to take my site that's up in here and I want to get it into the green zone. So there's two paths that, in order for us to do that. The path down means that I'm lowering the loading on the soil, and I can do that by reinforcement. The path laterally to the right is where I'm densifying the soil. I'm increasing the density, which means that I'm increasing the penetration resistance and moving the site over to the right. So the types of techniques that are going to densify the ground are stone columns, vibrocompaction, compaction grouting, and deep dynamic compaction. And the types of techniques that are going to reinforce the ground are deep soil mixing and jet grouting for the most part. I've seen a comment or two about drainage. Yes, drainage is another effect that helps to mitigate liquefaction. I think the current practice in the Western US is not to explicitly account for it. I think there's some concerns about the potential for fines migration and clogging during a liquefaction event. And there's just not as much research available on the subject of drainage. So we feel that there definitely is a beneficial effect to that, but we're not typically explicitly accounting for it in design currently, at least in the Western US, as far as I've seen. So vibrostone columns are very effective in densifying soils. We typically lay them out in a grid like this. The spacing and then the diameter of the columns and the type of equipment, the energy rating on the vibrator all control how much densification that you can get. And different contractors have different equipment, different methods, and it's sort of contractor dependent in terms of how much densification that you can get. Here at Keller, we have our own internal methods for estimating the amount of densification that we've, based on our experience. So basically, the further away that you get from the stone column, the less dense the soil is going to be. So a lot of specifications will have you testing at the center point between the columns, which is generally the worst point, the least dense point. And in a lot of cases, you may be more concerned from a design standpoint with the average soil properties. Like, for instance, if you're doing a slope stability analysis or a lateral spreading analysis, it's the average soil properties or the average soil strength that are going to dictate or represent basically the strength of the material as a composite when you're running your slope stability analysis results. So we encourage people to not just test the lowest spot or the worst spot in the ground improvement zone, but also consider testing other locations like halfway between the test one and the edge of the column, as shown in this diagram. This is some results on the left side. We have results from a compaction grouting project we did a few years ago, where we have the pre-testing SPT results, generally ranging from 5 to 23 or so. And after compaction grouting, the open circles are the individual SPT test results, and the gray triangles are like a running average of SPT tests. And you can see there was a threshold set here, and some of the individual SPT tests are just below that threshold. But in this case, again, this was sort of a stability issue, and we were more concerned with the average properties within the soil mass. So we came up with an average, a running average sort of technique to evaluate the specification compliance, and that was all those values were above. If you have 1 or 2 blow counts that are below a certain threshold, from an engineering standpoint, that's not going to be, most engineering cases, that's not going to be significant. So we encourage people to write specs where you're looking at averages if you're going to set some kind of threshold for penetration resistance. But even better than that, as a specification, we really encourage performance specifications in terms of calculated settlement values or displacement values for lateral spreading. On the right here is a paper from Boulanger and Hayden from '95, where they analyzed several Hayward-Baker compaction grouting sites, where they tried different grout takes, and you start off at a certain blow count, and depending on the grout take or the area replacement ratio, we got increases in the penetration resistance. So this is something that you can use to get a sense for how much improvement that you can get from compaction grouting. Soils. So what soils are densifiable? This is really a key element here. If you don't take anything else away from this presentation, I think this is probably the most important thing, because we see consultants recommending ground improvement, densification-based ground improvement techniques for liquefaction mitigation, but there are soils at the site that are just not densifiable because of their composition. And the reason that they're not densifiable is the same reason that a saturated clay, for instance, that's over optimum moisture content, can't be compacted very much. You have to get the moisture content right in order to be able to compact clays. But when we're talking about liquefaction mitigation, we're below the groundwater table, and it's 100% saturated. We just can't compact materials that have significant fines in them because they won't drain fast enough. So for CPTs, generally above I sub C 2.4, 2.5 or so, we have trouble with compaction. Fines contents more than about 25% or so, we have trouble, and then fines contents between less than 5% or so are readily compactable. You have a sort of transition zone in between, But we can do actually there's some things we can do, like using wick drains in between stone columns, that will really expand the range of soils into more fine-grained materials that we can compact. So there are different things that we can do, to affect the compactability. But generally speaking, these are the guidelines. So for shear reinforcement for stone columns, originally there was an assumption of strain compatibility in research that was done in the 1990s. If you assume that the strain is compatible between the soil and the stone columns, then you will calculate that that the stone columns take a large amount of the strain, the shear stress rather, and that there's a large reduction in the shear stress in the soil between the stone columns. There was, starting about 10 years ago, there was some additional work done at UC Davis and UC San Diego, where it was found that there is not strain compatibility. There's some bending in the columns that occurs, and that the effect of the reinforcement of discrete columns like this is a lot less than what we used to think. So the current research shows that the typical area replacement ratios for stone columns, which is on the order of 10% or so, and G sub R, which is the ratio of the shear modulus of the stone columns to the shear modulus of the soil, which is generally on the 5 to 10 range, results in, say, maybe a 5% reduction in the loading of the soil, which is really not that significant. For soil mix grids, however, since we can make them in panels, and they're very stiff, that this kind of configuration is very effective in shielding the soil in between the panels from loading. And so for area replacement ratios at typical area replacement ratios that we're dealing with for liquefaction mitigation of, say, 30 to 50%, you're talking about maybe an 80 or so % reduction in the shear stresses on the soil. So that can be very, very significant and an effective way to mitigate liquefaction. Okay, so settlement, meaning, bearing capacity and volumetric settlement. We have to worry about two things, as I alluded to earlier. Number one is a bearing capacity, which could lead to large settlements, tilting, collapse, that kind of thing. And then volumetric settlement, which occurs in the shallow layers, but also in the deep layers. So one question that comes up is, how deep does a liquefiable layer need before I start needing to worry about the bearing capacity being reduced? And there's a method by Meyerhoff and Hanna from 1978 where you have a footing bearing on a crust material that is relatively strong over a weaker material below it. And they've developed these bearing capacity equations, which can be adapted for liquefaction conditions where there's a layer at some depth, D sub L, below the bottom of the footing. And I normalized it. I ran these equations and normalized it by the footing width. And then on the x-axis here, you have the bearing capacity without any liquefaction, the bearing capacity with liquefaction divided by the bearing capacity without any liquefaction. So 1 means that basically there's no reduction in the bearing capacity. So if you have a layer that's like 3 times the footing width below a liquefiable layer that's at least 3 times the footing width below the bottom of the footing, then there's really not much reduction of the bearing capacity. But if you have a layer that's, say, 1 footing width below the bottom of the footing, you're going to be up in this zone, and that means that you're reducing the bearing capacity by more than half. So this kind of chart, these kinds of equations, if you use them, can give you a sense for when the bearing capacity issue becomes important and when you need to start thinking about mitigating liquefaction near a footing for bearing capacity. So it's important to note in high seismicity areas, we can't always design to eliminate all of the liquefaction. but we can design to increase the liquefaction resistance, increase the relative density, and increase especially the residual shear strength of the soil so that the bearing capacity part of it is taken care of. And when we evaluate bearing capacity, we're talking about, generally in practice, we're looking at the residual, liquefied residual shear strength. There's several methods available to evaluate that. But just to give an idea for those of you that might not be as familiar with these methods of what it means when a soil liquefies in terms of its shear strength reduction. These charts from Anderson Boulanger and Kramer and Wang 2015 are two of these examples of liquefied residual shear strength. Just for reference, with soft clay, we're talking typically of a shear strength ratio of about 0.25, maybe 0.3. If the soil has a blow count of 10 and it liquefies, then its residual shear strength can be on the order of 0.1, so more than a 50% reduction, and that's a pretty low shear strength. If you think of it in terms of shear strength instead of shear strength ratio, normally consolidated soft clays can have an undrained shear strength of 250 to 500 psf. And so you can see with a low blow count kind of sand, you could be easily in that 100 or 200 psf range. And you can imagine what the bearing capacity reduction would be if you have a footing setting on that material. So if we introduce ground improvement, even if the soil liquefies, there's still a chance that we can design the ground improvement to reinforce the soil and to still support the footings with adequate bearing capacity. But we need to look at we need to design and look at the failure mechanisms that can occur. So we need to look at shear strength through the ground improvement elements, and we need to look at, if it's for instance a stone column, what is the potential for that material to bulge, just like a triaxial test with low confinement. The columns can bulge. For bearing capacity with soil mixing grids, it gets a lot simpler, and it usually becomes a non-issue because soil crete is relatively strong, and the area replacement ratios that we need to mitigate the liquefaction are usually also sufficient to fully support the structures without any reliance on the soil in between the grids. So even if there is some liquefaction that occurs within the cells, we're still supporting the structure on the soil crete grids. We just need to check the DSM crushing strength and make sure that the seismic bearing pressures and the down drag are addressed, and that we have enough capacity to resist those things. Okay, so for post-liquefaction volumetric settlements, again, this is a way of looking, what are the relative changes that we see if we densify the ground versus reinforce the ground. So this is a chart from Zhang and Robertson, 2002, that's very popular for evaluating post-liquefaction reconsolidation strains. If you have a site that's up here in this red dot, say that it has a factor of safety of 0.8 or 0.9 against liquefaction, if you reinforce it, that means that you are going to increase the factor of safety without changing the density. So you'd be moving down here, and that's the way in which you would get less volumetric settlement. If you increase the density of it, you're going to move to the right, because by increasing the density, you're increasing the penetration resistance. And when the penetration resistance increases, you're also increasing its liquefaction factor of safety. So you're going to move down and to the right if you densify the soil. And these are basically the techniques that we use in design, where we run it for stone column analysis. We run the analysis without any ground improvement. And then we make predictions of how much ground improvement, how much densification and reinforcement that we'll get, rerun the analysis and compute the settlements and until we reach a target that we're designing for. And I'll show you an example of that a little later. Right here. So this is software that we use at Keller to evaluate ground liquefaction and ground improvement design. This is an example of a site where we are designing for stone columns to mitigate the liquefaction. I know there's a lot going on in here, but I'll kind of try to break it down for you here. The gray line is the existing condition in these plots, and excuse me, the blue and the gray line are the existing conditions in these plots. And then the orange dashed line is the prediction of the performance in the design after ground improvement. So if we break down and look at this site, you can see in the I sub C plot that we have some relatively clean sands that are densifiable, and then an inner bed of silt and clay that's not very densifiable because it's got too much fines, and more densifiable sand. When we make our predictions of what the densification can be and what the increase in the penetration resistance can be, you can see that we're predicting increases in the sands and not really any increase in the clays. The red line here is the cyclic stress ratio, and you can see that the solid line here is the cyclic stress ratio without any ground reinforcement. In this case, we're designing for an 11% area replacement ratio, and that's going to reduce the seismic loading because of the reinforcement effect by around 7%. So this 7% reduction, you can see, really doesn't do all that much for you in terms of moving the needle and changing the liquefaction factor of safety. But the densification, if I go back here, the orange line that you see here represents the increase in the cyclic resistance ratio due to the densification of the soil. And you can see that there's a big shift from its original state to the densified state, and a corresponding shift in the factor of safety that's calculated. So we're still at this site, this level of treatment is still not making the soil non-liquefiable per se, but it shifted it from a factor of safety of like 0.2 to factors of safety of like 0.75 to say 1.5 or so. And so that results in a decrease in the settlement profile, where we had 3 1/3 or so inches and gone down to about 1 1/3 inches of settlement. But most importantly, and we run this for all of our calcs, is that we look at the undrained shear strength. This plot right here is the liquefied residual shear strength. The blue line is before treatment and the orange line is after treatment. When you see a diagonal line like this, it means that the undrained residual liquefied strength is more than the drain residual strength, and so it defaults to the drain residual strength, which is a diagonal line that's proportional to the overburden stress. So you see a dramatic increase in the undrained liquefied strength, and that's going to take care of bearing capacity problems if you had any. So the next example here is a site that is quite silty. So we have silt and interbedded with clay through here. This is a site that's difficult to densify because it has so much fines. And so you see that if I run a stone column analysis, that I don't get very much densification. And you can see that in the increase in the tip resistance is really quite negligible. There's also a minor decrease in the cyclic stress ratio, just like before. You get a little bit of decrease in the settlement, but the liquefied residual shear strength is still very low, and the settlements are still pretty high at this site. You know, you had 7 inches of settlement, and now it's still 4.5 inches of settlement. So the stone columns are not a very effective technique for this particular site. And but what else can we do about it? So one option is deep soil mixing. So we're talking about the same silty clayey site with deep soil mixing. We're reinforcing the ground, so we're not doing any densification of the soil between the soil-crete elements. So there's no change in the tip resistance. Okay, that's fine. There's no change in the cyclic resistance ratio before and after treatment. But what is changing is the cyclic, should say cyclic stress ratio. So the cyclic stress ratio is being reduced by about 85% or so. And so the loading on the soil has come way down. The cyclic resistance of the soil hasn't changed, but the loading has come way down. And that results in a significant increase in the factor of safety. And basically no liquefaction, no settlement. There's a little bit of settlement that's left over here. That's, really the structure won't experience this settlement because it's going to be sitting on the soilcrete. And the soilcrete can be designed to take all of the loads without any support from soil that might soften a little bit in between. Okay, flow failure and lateral spreading. What I've covered up to this point is really more about supporting vertical loads from buildings. With flow failure and lateral spreading, we're concerned about slopes. And typically we're designing ground improvement buttresses to restrain the slopes from moving. So if you're there are kind of two layouts to consider. One is just a buttress by itself. A lot of times this is deep soil mixing because stone columns, deep soil mixing is much stronger and effective at resisting large forces associated with lateral slope displacements. But stone columns may be feasible, especially if we can densify the soil to the point where it's non-liquefiable or it has a high residual strength. The geometry of these things are typically like 80% or so of the depth. The width is about 80% of the depth. Another approach is to, if you have a building site, is to make the ground improvement for the lateral spreading resistance integral with the ground improvement for the foundation support. So that's a configuration like you see on the right. The steps in this kind of analysis are basically, looking at the global stability for slip surfaces that could go through the ground improvement. Then doing analysis where you take out the ground improvement and you put the force on there that would stabilize the ground behind it. You solve for this force based on whatever target displacement that you may have in a Newmark analysis or factor of safety and a pseudostatic analysis. And then you run basically a stability analysis with that same force on the ground improvement buttress itself and check for sliding and overturning. In a situation like this where you could have, you can improve everything out into the water sometimes on a free face situation, and you may still have the ground moving away and cracking and pulling away from your ground improvement. So you really do also want to check the edge stability. If there was a crack that was to develop, you want to check the edge stability and make sure that this thing can be, can support the structure without any support from the soil next to it. For some projects that are, more involved or more demanding, we can do nonlinear deformation analysis. This is for a site that we're working on currently in California, where we're running a FLAC model and using liquefaction and cyclic softening models to evaluate the performance of the ground improvement buttress. Questions come up a lot about changes in shear wave velocity when you have ground improvement. There were some earlier estimates of how that could be how the shear wave velocity would change. And so this V sub S average over V sub S is basically the increase in the shear wave velocity from the existing one at the site. If you base it on an area weighted average, you'll get the lines in red, but those have been shown to be incorrect by recent research, which I've cited down here at the bottom. So for columns of ground improvement with G sub R's of 5, 10, and 20, you see the kind of increase in shear wave velocity. So for instance, for stone columns where your replacement ratio is around 10%, you're looking at pretty modest increases in the shear wave velocity, maybe like 10%, not very much effect. Conversely, if we look again at soilcrete panels, where you have area replacement ratios that are like 30 to 40%, for G sub R of say 20 or so in here, you're talking about the ability to maybe double the shear wave velocity over the interval of treatment. So the takeaway here is that you can get significant shear wave velocity increases with soil grid panels, but not so much with columns, even if they're made of soilcrete, which is a G sub R, maybe 20 to 50. Still, the increases are, at least for low area replacement ratios, are pretty modest. I put the equations in here since some of these references aren't really widely available. Quality control and quality assurance are very important aspects to any ground improvement method. At Keller, we use data acquisition systems on our rigs to make measurements of the rig's response. For stone columns, we're measuring depth, we're measuring current draw from the vibrator, air pressure for injecting air. And we can make plots of the work, which is the amperage times time versus depth, to check to make sure we're putting sufficient effort into it. Then we can also make estimates of what the diameter of the column is based on how much volume of rock that we're putting in the soil. Whenever we add a bucket of gravel into the hopper, that's a known volume, and we know where we put that in the ground, so we can make these estimates of the diameter of the column. So this kind of helps with quality control during construction, but ultimately, if you're doing a densification project, you really should be doing post-improvement penetration testing to check to make sure that you're getting the densification that you assumed would occur in your design. And so that's a fairly straightforward thing. On the right side here, you see a cone penetration test that was done before the ground improvement, and with the gray line, and then the orange dashed line is after ground improvement, and you can see the increase in the resistance. One thing to be aware of is that you can see changes in the I sub C between the before and after CPT tip resistance, and it maybe that there's not a change by densifying the soil. You're not changing the gradation of the soil, so there really should be no change in the I sub C, and sometimes it's required to manually shift the post I sub C over so that it matches the pre I sub C. And there's a paper on that I wrote with a couple of colleagues, and it's an option that's available in CLIC, for instance, commercial software. For deep soil mixing, we also have data acquisition systems where we measure several different parameters on the rigs. Most importantly, we're measuring and monitoring the blade rotation number, which is the number of rotations of all the blades over a 1 meter interval. So here the red line is the BRN, and that's running around 600. So 600 passes of a blade around in a circle over a 1 meter interval. So just to give you an idea of how much mixing energy goes into mixing the grout with the soil. And then our rigs are also equipped with the automatic pumps so that we get a nice consistent dosage level of cement binder in the ground. So if the drill rig has to slow down to penetrate a harder layer, the pumping rate will slow down with it so that it maintains the target dosage of cement binder. Conversely, if it were to speed up, it would pump faster to keep that same dosage rate. And then, of course, we do coring after the columns are set. We do wet grab samples where we put a little trapdoor bucket down into the column and grab a sample and cast it in cylinders. We do unconfined compression testing to evaluate the strength of the material and make sure that we meet the minimums. And these unconfined compression tests, just like with concrete, and as it cures with time, you'll get an increase in the compressive strength, and that should be accounted for in design. If you are going to base your testing at 28-day strengths, if you're designing for an earthquake that has a low probability of occurrence, say in the first 6 months or year of the project's existence, it's justifiable to design for the strength gain that you would get, over a 6-month or maybe a year period. And there's some equations for that, for estimating that in the FHWA DSM manual. Rigid inclusions are a relatively newer technique. I'm going to kind of skip over this for the sake of time. There's some ongoing research that's been sponsored by DFI, but just these are slender, relatively rigid and brittle elements that haven't really been proven for liquefiable soils yet. So they should be used with caution if they're used at all on any liquefiable sites. I have the references for everybody in case you're interested in the references. You can email me and I'll send them over to you. That's about it.
Thank you, Jim. I had to find my unmute button there for a second. Seems like a common occurrence. I want to remind everybody that there's going to be posted, it's posted right now in the chat box, that a form that you just need to fill out and submit to get PDH credits for this presentation. And with that, we have about 7 minutes left before the hour. So Jim, if you'd like to go ahead and look at the chat and start working away at the answers to the questions, that'd be great. And to remind everybody, there are a number of questions. We won't have time for all of them. So we'll follow up. We'll have a follow-up email with the answers to those. Go ahead, Jim.
Okay, good. Let's see. The one question is, will the slides be available? I don't think we're going to distribute the slides, but I think there may be a recording available. If you contact us, you'll be able to give you access to a recording of the presentation. Let's see, there's another question. What is the minimum depth of overburden and jet grouting to be effective and no heave of the ground? It's not so much an issue with jet grouting. You can probably do jet grouting within just a meter or two from the ground, or even up to the ground surface. It's more of a safety issue with the jet, coming up out of the ground. It's not like compaction grouting where you need at least 10, 15 feet of overburden pressure. Somebody asked to touch on earthquake drains. I'm sorry, I just don't have enough time to cover that. Let's see. Let's see. Any negative effects to applying one of these mitigation actions besides cost? Well, you have to, potentially, yeah, you have some practical issues like when you do stone columns or vibro compaction, you can get settlement of the ground. And that can extend out around the locations where you're treating. So if you have settlement sensitive structures and you're doing work next to them, you need to be careful, things like that. Compaction grouting can have some, grout likes to go in strange places. It works its way into interesting places. So if you're doing compaction grouting or jet grouting, you need to be careful if you have things like pipes nearby that might be affected by the grouting. Let's see. Anyone? We already covered that. How to determine the bearing capacity by bulging failure mode of liquefiable soil. So there's a method that's available for that. If you email me directly, I can provide you a reference. How do you account for the duration of shaking in your liquefaction mitigation analysis? And number two, how do you account for sloping ground and potential permanent offset in the ground at the end of the shaking? So the duration of shaking is, at least as far as liquefaction triggering goes, is encompassed in the magnitude scaling factor. Some other methods, like if you're doing a lateral spreading method, most of those have a magnitude factor that accounts for duration in it as well. For instance, like Bray-Macedo method for lateral slope displacements, or Brain-Travassaro. And then how do you account for sloping ground? That there are also methods for accounting for the sloping ground. For triggering, there's a K alpha effect that can be used. You can find that in the Youd et al. 2001 paper. It's not frequently used in practice. It should be used with caution. But as far as like stability analyses, they all have some way of accounting for the sloping ground. Could you explain how methods code you're reducing PGA using reinforcement? You can find that information in the references. It would be Nguyen et al. This one, Nguyen et al. And these Raimaji papers will explain the reinforcing effects. I can send you the list of references so you can find those things. Let's see. Could you provide the references on estimating improvement of VS after improvement? Yeah, please email me and I can send you what you're looking for.
And I have included Jim's email in the chat as well.
Yeah, just please be patient since there might be quite a few requests for me to respond to. A lot of people interested in getting the slides. Can you please comment further on the calculation of bearing capacity, including ground improvement with the stone columns? So again, there are some methods. We use the same methods that for static bearing capacity that are available. And we just use a liquefied residual shear strength typically for evaluating bearing capacity with stone columns. Again, if you contact me, I can give you some more specific references. I don't have it all, sort of queued up and ready to show here. You consider deep soil movements estimated from numerical modeling and defining depth of treatment, or you may consider a threshold depth of expected kinematic lateral displacements as function of height of slope ground. Some may limit displacements with 18 meters depth. If we're doing a numerical model, usually that's a performance-based design approach, and I'm not going to arbitrarily cut off the analysis at a certain depth as long as the model is valid for those depths. And if you're going to the trouble of doing a numerical model, I think they can easily be extended to 18 meters or more. So I wouldn't arbitrarily cut something off. But it is true that sometimes, especially with a level ground site, that what starts occurring at greater and greater depths might not be of much engineering significance near the ground surface. So it's something to consider in your design. We're right at 12. There are quite a few more questions left. So
yeah, Jim. Yeah, I think we're probably going to need to cut it off. You'll be here all afternoon if you try to answer them all.
Yeah.
So But what we will, we do have recorded the questions, and we will answer those in a follow-up email. Jim will, I won't. um, so Kelly has posted in the chat Jim's email address. So if you have questions you think of after this presentation, please submit them to Jim or through LinkedIn. And that is our presentation for today. Thank you for attending, and we hope you found it enjoyable and beneficial. Thank you, and stay safe. Bye-bye.
Thanks, everybody. Appreciate it.
You there, Kelly?